Let's talk about collision detection and resolution algorithms a little bit. If you are serious about game development and related fields, I believe it is absolutely crucial to know this stuff. Even if you never have to implement these algorithms yourself, having a deeper understanding of how they work under the hood is an advantage. For simplicity, I will discuss these algorithms in 2 dimensions, but they translate to 3D quite easily. Let's start with the easiest one, detecting and resolving collisions between 2 axis-aligned rectangles. Axis-aligned rectangles have their edges parallel to the x and y axis. First, find the distance between the centers of the rectangles on both x and y axes by calculating the absolute difference between the x and y coordinates of these centers. If the horizontal distance is less than half the sum of the width of the 2 rectangles and the vertical distance is less than half the sum of the heights of the 2 rectangles, then the rectangles intersect. To resolve this collision, we need to know how far to push the rectangles away from each other. We already know the distance between the rectangles on both axes and how far apart they should be. Subtracting the actual distances on the axis from the desired distances gives us the amount by which we should push the rectangles away from each other on the respective axes to solve the collision. We only want to push them away from each other on one of the axes, not both, because pushing them on both axes will result in the rectangles touching each other's corners, which is not the desired behavior in most applications. Using the axis with the least penetration distance to push away makes the most sense. It's up to you to decide which rectangle should be moved and which should stay in place. You might even choose to move both equally or based on some physics logic. Next, let's look at circle versus circle collision. It involves a bit more advanced math, but nothing too scary. This problem can be viewed as vectors problem. Subtracting the center coordinates of the circles will give us a vector pointing from one circle's center to the other circle's center. The length of this vector is the distance between the circles. If this distance is less than the sum of the radii of the circles, then they overlap. To calculate the length of the vector, we can use the Pythagorean theorem, which states that the squared length of the hypotenuse is equal to the sum of the squared lengths of the sides. The hypotenuse is the length of our vector, and the sides are its components. Taking the square root of the sum of the squared sides length gives us the length of the hypotenuse and thus the length of the vector. If we increase the length of the vector to make it equal to the sum of the circle's radii, we get the vector that points from one circle's center to the point where the other circle should be to avoid overlap. To do this, we multiply the components of the vector by the quotient of the desired and actual lengths. If we add this vector to the coordinates of the first circle's center, it will give us the resolved coordinates of the second one. Similarly, we can subtract the vector from the coordinates of the second circle to get the resolved coordinates of the first one. Surprisingly, we can combine these 2 methods to detect and resolve collisions between a circle and a rectangle. If the center of the circle is horizontally between the left and right sides of the rectangle or vertically between the top and bottom sides, we can use a simplified approach. Imagine the circle as having a bounding box and use the rectangle versus rectangle detection and resolution method, treating the radius of the circle as half the width or height of a square. Otherwise, we can treat the closest corner of the rectangle as a circle with a 0 radius and use the circle versus circle method to stop the circle from penetrating the bounds of the rectangle. These are just the most basic collision detection and resolution algorithms. We will talk about more advanced ones in the future videos, but even these simple algorithms can take you very far in implementing collision detection and resolution in your games and simulations. I am intentionally leaving out the exact code implementation from this video. Trying to implement these methods yourself can be hugely beneficial. See you in my next video. Bye!